Hello and welcome to Tech Simplified TV. We all know IC manufacturing is a time, labor, research and money extensive process. Although there are some physical and electrical reasons which can spoil the whole process and lead to IC failure. In today's episode, we will talk about reliability in CMOS and try to understand the reasons which can lead to IC failure. So if you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, what is reliability? Next, reliability factors. There are 2 slides on this topic. Next, time dependent dielectric breakdown, negative bias temperature instability. On NBTI, we have 2 slides. Next, hot carrier injection, soft error. There are 2 slides on this topic. After that, electromigration. Next, self-heating. Next, stress migration. After that, CMOS Latchup. And finally, electrostatic discharge. All these topics starting from time dependent dielectric breakdown or TDDB to electrostatic discharge, these are phenomena which actually lead to chip failure. So we are done with this slide. Now let's move to the next slide. So we are done with this slide. Now let's move to the next slide. What is reliability? Let's define reliability. Reliability means how likely it is that a product or system or service will work well for a certain amount of time or under specific conditions without any issues. Reliability is related with the performance of a product or system or service. It means when we have a system or product or service, by reliability of that product, we understand that whether it will work properly or not. Properly means for how long it will work and whether it will work under specific conditions without any issues or not. There are few terms are related with reliability, like probability of success. How likely it is work well, that means whether it will be successful in serving its purpose or not. First is probability of success. Next, durability, whether it is durable or not. Dependability, can we depend on its result or its performance? Quality over time. In definition of reliability, always there is a time factor. Availability to do its job. So failure is deviation from compliance with the system specification for a given period of time. We will call a system it's a failure if it failed to perform in a specific way for a period of time. Failure can happen for different types of faults. Reasons might be design bugs, manufacturing defects, or wear out of oxide or interconnect, or external disturbances or internal malhandling of a product. Although not all fault leads to errors. It's not always that any fault is there and it will lead to error. Although sometimes faults lead to errors. And that different kind of failures can happen because of manufacturing defect. While it's getting manufactured, there is a defect. Design bug, bug was there and it has been overlooked. It was not properly solved before release. And wear out of oxide or interconnect. Instead of our chip, we use 8 to 10 layers of metal interconnect. So wear out of oxide means disconnection of a portion of the circuit or the chip. So it will lead to failure. If gate oxide gone through breakdown, then the circuit will not work properly. So these might be some reasons. A number of physical failure mechanisms that can affect the reliability of a CMOS ASICs. There are some reasons which lead to failure. Now, yield and reliability are 2 most important aspects for development of new technology. A new technology, if its reliability factor is not high, yield is not high. Yield means if we are manufacturing n number of chip, how many of it coming out good, not rejected. Obviously, when we are manufacturing n numbers of chip, we always want most of them to work. It get used and then it's sold in market and the money get recovered. And reliability, even after selling, whether it's working properly or not. Designing a reliable CMOS chips involve understanding and addressing of potential reasons of failure. We must analyze and understand what could be the potential reasons of failure so that we can give some safeguard. If we overlook all those conditions, so there is a huge chance that it will lead to a failure. So here is a table failure factor versus failure mechanism. Bulk is a failure factor and mechanisms are crystal defect. Crystal could be defective. There could be crack, surface contamination, surface of the wafer could be contaminated, junction deterioration, impurity precipitation, mask deviation. These are bulk related mechanism. Now comes oxide film. Interface state. Oxide is an insulator. There should not be any free charge. An oxide is a good oxide if it is highly non-conducting. There is no state, free state, no interface state. In practical, it doesn't happen. There are some interface states. Although number of interface states must be within limit. Otherwise, the quality of the oxide film is not considered for a good MOSFET. Interface state, quality of oxide film, time dependent dielectric breakdown, hot carrier, negative bias temperature instability. These are the issues related to oxide film. Now metallization. After oxide is deposited, then metallization is done. For metal, electromigration, self-heating, stress migration, these are three mechanisms which leads to failure. And environmental, there are some environmental factor also like static electricity, over voltage, surge voltage, latch up, soft error. This static electricity leads to basically ESD, electrostatic discharge. We already have a separate video and article on that. Link is provided in the description. In this discussion also, we will briefly discuss it. So we are done with this slide. Let's move to the next slide. Now reliability factors. What are the factors related to reliability? If a device is under wrong use condition, a failure may occur. Reliability of a device depends on how much stress it can handle. Some factors related to failure are electric load, temperature, humidity, mechanical stress, static electricity, effect of repeated stress. A device not only get damaged because of its manufacturing defect or material defect, it can also get damaged because of handling, rough handling or malhandling. If a device is used under wrong use conditions, a failure may occur. Wrong use condition, wrong handling, these are basically create stress on the product or the device. How much external stress it can handle, that decides whether the device is reliable or not. So some factors related to failure are electric load, temperature, humidity, mechanical stress, static electricity, effect of repeated stress. So electric load. Operation conditions determine life of semiconductor devices. Electric power causes a rise of junction temperature which might lead to device failure. Under which operation condition a device is getting used, that determines life of that device. Electric power can create a rise of junction temperature which might lead to device failure. The electric current should be lowered as far as possible. In most of the electronics devices, electrical limit is mentioned. Voltage and ampere ratings are there. If we do not follow that rating while giving its charge or using it, then device can get damaged. So it's necessary to handle the surge current that flows when the switch is turned on or off and surge voltage of inductive load so that they do not exceed maximum rated values. And many times we have seen in case of home appliances, for sudden surge of electricity in our regular electric line, home appliances get damaged because of this surge of current. For every device there is a rating specified. The surge current is obviously much higher compared to that, and that leads to failure of the device. Temperature. Temperature affects the life of semiconductor products. A rapid or gradual change results in deterioration of characteristics leading to device malfunction. So temperature can affect the device performance and its lifetime. The relation between life L and temperature T is this one. It's an exponential relationship. This is life and this is temperature, absolute temperature. The life will be shortened if temperature rises. A ventilation device or heat radiation device used to avoid overheating issues. Now humidity. Usually IC chips are covered with surface protective film to protect from humidity. If a device is operated under severe humidity condition, it should be operated particularly carefully. Protective film is there to protect the chip. Humidity, that is moisture present in the atmosphere. If the operating condition is humid, we must be much more careful about it. We are done with this slide. Now we will move to the next slide. Now reliability factors. There is another slide on that topic. Mechanical stress. If the device is strongly vibrated during transportation or of an extremely strong force is applied to a device during installation, the device may be directly mechanically damaged. In addition, moisture or contaminant may enter the device through the damaged area and may cause deterioration of the device. Now static electricity. Electrostatic charge damage the equipment. Equipment incorporating device is often charged with static electricity. In some cases, and recently, plastic is generally used for casing and structure equipment. Human bodies can also be charged with static electricity. While handling semiconductor devices, it's necessary to take static charge preventive measures. These issues become more serious as device dimensions are aggressively scaled and operating frequencies moving higher. Static electricity is also a damaging thing. It can damage equipment, and human bodies carry static electricity. If we do not handle it properly, it can lead to damage and failure. So we need to take preventive measures. And finally, effect of repeated stress. If a stress is repeatedly applied, it might be stronger than steady stress. A high low temperature cycle and intermittent internal heat generation cycle can apply stresses repeatedly. The effects of such cycles, such as rearrangement of material structure and fatigue, deterioration of resistance to distortion, are examined and utilized for evaluation of failure. Steadily a stress is there and intermittently a low valued stress is applied. Continuous application of stress, multiple cycle of stress can lead to failure also. It's not that always strong steady stress will lead to failure. Suppose for a product or a system, high low temperature fluctuation or cycles are there. So that also can lead to failure. So we are done with this slide. We will move to the next slide. Now failure mechanisms. First mechanism is time dependent dielectric breakdown or TDDB. Gate oxide thickness has reduced with technology nodes. Electric field across TOX is getting ever stronger. Oxide film breakage is caused by an initial defect, deterioration of the oxide film. So two types of situation may arise. That an initial defect is there in the oxide layer or deterioration over the time it got deteriorated. Initial defect lead to an early failure. Early failure means process of failure has got initiated from very early use. Now deterioration of the oxide film leads to long-term reliability failure. That is, gradually the oxide film or oxide layer is getting deteriorated and its performance is degraded and finally reliability failure occurs. Oxide layer breakdown, if applied electric field exceeds dielectric breakdown, withstand voltage. If we applied for any oxide layer a field which exceeds breakdown withstand voltage, it will break down. Second point is, even if the electric field with lower value is applied for longer period of time, that may also cause breakage as time elapses. If the electric field has lower value, it's applied for a longer period of time, that also leads to breakage or breakdown of the dielectric layer. This type of breakage is referred to as time dependent dielectric breakdown. That is, it's not instantaneous, it will take time and time dependent. Time is a great factor here. There is an empirical formula which describes the TDDB life, how long it will take. T life in practical use, TT life in test, beta electric field acceleration factor, this beta, and E is electric field strength in practical use, electric field strength in test, activation energy, Boltzmann constant, temperature for actual case. So from this equation we can easily realize that temperature dependency is there and time dependency is there. So TDDB is a time dependent, as the name suggests, it's a time dependent phenomenon. Effective methods to prevent these failures are optimizing the process in order to minimize variability, formation on oxide film with less defects, screening by use of high electric field during inspection or burning, testing showing some trap points are there, and as we know, if close enough, so basically it creates a conduction path through the oxide layer. This is the diagram. We are done with this slide. We will move to the next slide. Now, negative bias temperature instability. There are two slides on this topic. To understand it, we need to understand the situation over this region. This is the silicon layer. Silicon dioxide layer is here, and now metal. This is the basic MOS structure. Metal oxide semiconductor. Here we can see some charges are there. First we will try to understand the scenario, and then we will come to the physics of NBTI. 4 types of electric charge exist in gate oxide films. We need to know that because these charges play a very important role in this phenomena. Mobile ionic charge QM, fixed oxide charge, interface trapped charge, and oxide trapped charge. NBTI is an increase in the absolute threshold voltage, a degradation of the mobility, drain current and transconductance of P MOSFETs as either negative VG or elevated temperature. Due to NBTI, there are bunch of parameter value degradation happens of a MOSFET: mobility, drain current, transconductance, threshold voltage. These are some important parameters related to a MOSFET. This bunch of parameters get degraded in case of negative bias temperature instability or NBTI, and it creates an instability. From the name, 3 things we can understand. One is negative bias, temperature, and instability. And for these 2 parameters, this instability basically occurs. So that happens with P-type MOSFET at either negative voltage or elevated temperature. A stronger and faster NBTI effect is produced by their combined action. And in case of stronger and faster NBTI effect, it will happen quickly, and even with great degradation, that will happen if these 2 factors, that is negative bias and temperature, they both of them come into play. So such fields and temperature are typically encountered during burn-in and during routine operation in high performance ICs. During burn-in, that can also happen, and during routine operations of high performance ICs, that can happen. Why it happens? Silicon has 4 valence electrons, that is 1s2, 2s2, 2p4. We know that. At the surface of silicon crystal, atoms are missing and traps are formed. This is the silicon. These valence electrons are shared between 2 silicon atoms. We know that. These positions at surface, atoms are missing, and here traps are formed. Density of these interface states, that is defined by DITUs. When we do the oxidation, most of the interface states are saturated with oxygen atoms. This free, open, and this missing electron missed or trap kind of situation reduced. We tried to show in this diagram. Here 5 atoms, 1 electrons are missing here. Bond with another atoms is missing here. Here oxygen atoms are there. To reduce the number of dangling valence bonds, here dangling bonds are still present. Here after oxidation, number of dangling bonds reduces, still present, quality improves. To reduce the number of dangling valence bonds further, surface is annealed with forming gas. That's a mixture of hydrogen and nitrogen. That hydrogen make a bond with this silicon. These dangling silicon bonds are pacivated by forming silicon hydrogen bonds. The number of electrically active interface states can be reduced to acceptable range. Now these dangling bonds reduced and it reaches an acceptable range. These silicon hydrogen bonds have lower binding energy. Elevated temperature and high electric fields break these bonds and interface states reactivated. Their binding energy is low. If temperature is elevated or high electric fields are there, these bonds just break. The exact properties of interface defects, which are trivalent silicon atoms with 1 unpaired valence electron, depends on exact atomic configuration and orientation of the substrate. Holes interact with silicon hydrogen bond and weaken silicon hydrogen bond. Now, for a PMOS, at elevated temperature, silicon hydrogen bonds dissociate. Like silicon hydrogen, one hole is get associated with that, it becomes positive, becomes a ion, and this bond is broken basically. The effect bias temperature instability can be observed in both P-channel and N-channel MOSFETs. However, P-channel MOSFETs with negative VG stress are more susceptible to this kind of degradation. In a P-type MOSFET, in P-channel MOSFET, holes create the channel when negative bias is applied. Like N-channel device, to create a channel, we need to apply positive voltage at the gate electrode, and for P-channel MOSFET, we need to apply a negative bias to attract the holes. When negative bias is applied, holes are coming close to the interface silicon dioxide interface. There is those dangling bonds and the silicon hydrogen bonds are there. Holes are attracted there. They weaken those interface states, again reactivates. It has been reported for NBTI degradation, channel cold holes are important. As N-channel MOSFET biased into accumulation also has holes at the surface of the substrate, the threshold voltage shift should be similar to P-channel MOSFET. Therefore, the lack of holes cannot be the cause for different degradation behavior. Presence of hole is the creating his situation here. When we are operating N-channel MOSFET in accumulation, we are applying negative bias that accumulates holes near the interface and creates similar situation. The effects on circuits occur primarily in P-channel MOSFET with negative gate voltage bias and is negligible for positive gate voltage. Usually occur because negative gate voltage is required. At gate voltage, if we apply negative voltage, holes are attracted towards the silicon dioxide interface, and here that silicon hydrogen bonds are there. So that bond having lower binding energy, that weakens by hole interface states, they again reactivated. Usually occur during high state of P MOSFET inverter operation. Leads to timing shift, potential circuit failure due to increased spread in signal arrival in logic circuits. Asymmetrical degradation in timing paths can lead to non-functionality of sensitive logic circuit products, field failures. If a circuit cannot match its timing, it's not reliable because a circuit has its purpose. It's designed in that way to match its timing. It cannot do the matching, then it's not working in proper way. So we are done with negative bias temperature instability, and now we will move to the next slide. Hot carrier injection. That is another phenomena that leads to failure. Hot carrier injection is one of the most significant problems regarding reliability of state-of-art MOSFET. It's an important issue, although in state-of-art MOSFET, that means small dimension or reduced dimension MOSFET, this situation is even worse. It's difficult to reduce the power supply voltage. We are scaling this thing, but power supply voltage scaling, that's a tricky situation. For DSM, that is deep submicron and nano devices, electric field strength is increasing. Devices are getting smaller, and along with that, we cannot scale the supply voltage with same scaling factor, so field is high. Hot carrier is a generic name for high energy hot electrons and holes generated in the transistor. Hot carrier injection into gate oxide film generate the interface state. If hot carrier injected into gate oxide, it generates some interface state in oxide layer. And fixed charge, they do not move, but there are fixed charge, and if number of fixed charge is high, that will lead to deterioration of the dielectric layer condition or its property and lead to failure, breakage and failure. And finally deteriorate the VT and GM, that is transconductance of the MOSFET. As the VT of the FET is increased, the circuit operation will become slow and will finally operate abnormally. VT is high. It will take higher voltage to turn on. It will take more time to turn on. So if it takes more time, the circuit cannot match the final timing. Hot carrier is easily generated when VG is less than VD by 2. That means VD is much much higher than VG. That is, VG is less than half of VD. When VD is much greater than VG, the carrier present in the channel will impact the silicon crystal lattice. From here, if VG is not that prominent, very less, and VD is really high, so electrons which are flowing from here to there, they become highly accelerated. Once they are accelerated, they impact the lattice. Their impact with lattice creates, and more they are going towards drain, the field is higher, so their acceleration increases. Their impact with the lattice, that creates electron hole pair. Here, electron hole pair created. Those electrons are attracted here. If it's impact in oxide, it will move through the gate oxide layer, and the holes are attracted toward base. When VD is greater than VG, the carrier present in the channel will impact the silicon crystal lattice and generate pairs of hot electron and hot hole, that is impact ionization. These pair functions at hot carriers. And now they are working as hot carriers, high energy carriers. Hot carriers under strong VD gain enough energy to break the barrier of silicon dioxide interface and go through the gate oxide into the gate. As a result, either the gate oxide film is charged or the silicon-silicon dioxide interface is damaged. These lead to change in transistor characteristic. Hot carriers are generated and now VD is high enough to break the barrier of this silicon-silicon dioxide interface and go through the gate oxide into the gate. If it overcomes this barrier of silicon-silicon dioxide interface and move through this oxide to gate oxide, it's getting gate current and silicon-silicon dioxide interface is damaged. At device level, the performance gets changed. Generation mechanism of hot carrier, there are three types of. One is channel hot electrons, avalanche hot carriers, and substrate hot carriers. Among these three, AHC or avalanche hot carriers, this is most important, create remarkable change when devices are miniaturized. So that is hot carrier injection. Here this SHE, CHE and HC hot carrier injection are shown. We are done with this slide. Now we will move to the next slide. Now soft error. There are two slides on this topic. A very small amount of radioactive elements are present in the package material. We fabricate a chip, we need to properly package it. So in packaging material, a small amount of radioactive element like uranium or thorium, these are present. A small amount of radioactive material is present, so obviously alpha particles are radiated from it. So abnormal operations of devices is caused by alpha particles radiated from that radioactive element. This problem is referred as soft error. This abnormal operation is temporary, so writing data again can restart normal operation. It's very significant for memory devices. We use memory devices storing data there. So once its data is there and alpha particles change that data, so when we want to retrieve it, that give erroneous result. This problem is more dominant in advanced node devices. In this dimension, the electric charge of signals handled in devices is lower because device dimension is lower, so operating voltage is also got lowered. Now electric charge of the noise generated by alpha particles that are radiated in the chip has a large impact that cannot be ignored. The operating voltage is less. Now this electric charge of the noise that is generated by alpha particle that become quite significant at this dimension. The alpha particles are generated at the cell capacitor that stores 1 bit data, 1 bit minimum data unit of dynamic RAM. We have mentioned that it's more important for memory devices. The alpha particles generate electron-hole pairs in the substrate. Alpha particles lose their energies in the generating the electron-hole pairs. The electron generated in the process can invert the data of the cell capacitor. The alpha particles has its energy and that energy creates electron hole pairs in the substrate. In this process, extra electrons are got generated because of these alpha particles. A cell capacitor is considered low if electron exists and considered high if electron do not exist. If it's in high state and because of alpha particle, these extra electrons are there. So it initially didn't have electrons, so it was in high state. Now electrons are there, so it becomes low state. So state is changed. If electrons are generated in the cell capacitor by alpha particles, data H will be inverted to data L. This is referred to as soft error in the memory cell mode. Soft errors affect memories, registers and combinational logic also. Memories use error detecting and correcting codes to tolerate soft errors. So these errors rarely turn into failures in a well-designed system. Since we know this error might happen, so there are detecting and correcting codes that's used for memories so that it doesn't lead to failure. We are done with this slide. We will move to the next slide on this topic. The cell capacitor data is read out by bit line by diffusion and then compared with the reference potential. If electrons generated by alpha particles flow into the bit line, the potential of the readout data or reference potential may be lowered. If the data potential is lowered, data will be inverted from high to low. If the reference potential is lowered, the data will be inverted from low to high. So this extra generation of this extra electron and where it flowing, depending on that, the state is get changed. Because the cell capacitor data is read out by the bit line by diffusion and then compared with the reference potential. It's determined by comparing with the reference potential whether the bit line is at high or low, that is determined. Now, if the generated alpha particles flow into the bit line, so electron is there, so potential of the readout data or reference potential get lowered. Electrons are there. If the data potential is lowered, data will invert it from high to low. If the reference potential is lowered, the data will invert it from low to high because comparison is there. We are doing a comparative study. So the reference potential, if it's get lowered, the data will become higher. This is referred to as soft error in the bit line mode. If the operation cycle or cycle time of the dynamic RAM is shortened, the reference potential will be compared with the data potential more frequently. As a result, soft errors in bit line mode will be increased. On the other hand, change in the cycle time will not affect the soft errors in memory cell mode. So we can handle it this way. Now, prevention of soft error: to use package material that contains less radioactive element, alpha particle generative source. If we use a package material which has less radioactive elements, that will solve the issue. To prevent alpha particle from entering the chip by coating organic material on the chip so that it cannot enter the chip. Improvement of the bit line structure using wire materials of aluminum, polysilicon, etc. Improvement of sense amplifier, adoption of return bit line, etc. There are methods to prevent soft error. They are done on soft error. We will move to the next slide. Now, electromigration. We already have 3 episodes on electromigration. Link is provided in the description. You can watch the video. Here we will briefly discuss about electromigration. While operating, a chip may go above 100 degrees Celsius during practical operation. High frequency power loss and consequent heat dissipation contributes in increased temperature. Rise in temperature enhances solid state metal ion diffusion. Continuous current flow is happening through this interconnect, and when current is flowing, heat is get generated. If proper design considerations are not there, ions in interconnect, they can diffuse. Once they move from their position, that create a void. That means disconnection or open circuit. If connectivity is not there in between conductor, it's open circuit. Either open circuit void situation may happen, and since it's at micro level, they're very close to another interconnect, so it can move from its position and can touch the other. If it touches another interconnect, then it's creating short circuit. So electromigration is caused by scattering of moving electrons with the ions by momentum transfer between electrons and ions in metal interconnect. This ion-electron interaction is sometimes referred to as electron wind. This causes wire to break or to short circuit to another wire, just what I have discussed. Such situation, void in interconnects, can lead to open circuit, that is chip failure. EM is one of the most menacing and persistent threat to interconnect reliability. Mean time to failure due to electromigration, that is MTFF, this is the expression. It means mean time to failure, constant of wear, current density. MTFF is proportional to current density, and the following factors can reduce the failures caused by electromigration: crystal structure, grain diameter, crystal orientation, addition of another elements to metal film, laminated wiring structure. These are usually followed to prevent from electromigration. Now, electromigration depends on the current density J. It's more likely to occur for wires carrying a DC current where the electron wind blows in a constant direction than for those with bidirectional currents. So, wires carrying DC current or one directional current, electromigration is predominant thing, and we need to consider some design specification to get rid of electromigration or EM. We are done with this slide. We will move to the next slide. Now, self-heating. Bidirectional wires are less prone to electromigration, although their current density contributes in by self-heating. High current dissipate power in the wire. If high current is flowing, it creates heat. Since surrounding oxide or low K dielectric is thermal insulator, the wire temperature can become significantly greater than the underlying substrate. So around interconnect, there are low K dielectric. Dielectrics are electrical insulator and they are thermal insulator also. So they do not carry away that heat. Continuously heat get generated and that cannot get dissipated. So hot wire exhibit greater resistance and delay. We know that property. Electromigration is also highly sensitive to temperature. So self-heating may cause temperature-induced electromigration problems in the bidirectional wires. Electromigration is sensitive to temperature. We have seen that equation. So here, if continuously temperature increases, it can lead to temperature induced electromigration also. So brief pulses of high peak currents may even melt the interconnect. Since brief pulses of high peak current create huge temperature that might melt the interconnect. A significant percentage of device self-heat energy flows vertically and laterally to the interconnect layer. The local temperature rise depends upon thermal dissipation paths away from the heat energy originating element. Self-heating is dependent on the root mean square current density. So depend on current density. Self-heating is also dependent on IRMS. Temperature of any point in the chip depends how far from the heat generating point or heat generating element, depend on that. A conservative rule to control reliability problems with self-heating is to keep JRMS 15 milliampere by Rm square for bidirectional aluminum wires on silicon substrate. So the maximum capacitance of wire can be estimated based on the IRMS current. Current must be at lower side. There is a calculation and we must follow that. Electromigration from high DC current densities is primarily a problem in power and ground lines. Self-heating limits the RMS current density in bidirectional signal line. So this is self-heating effect. Self-heating effect can also lead to electromigration and failure. So we are done with self-heating effect and we will move to the next mechanism. Stress migration. Stress migration is another failure mechanism. Stress migration or stress-induced voiding is wear-out failure mechanisms in chip metallization. It causes an open circuit in the metal interconnects, especially at the via, since it is the weakest link. Stress migration is caused by interaction between thermomechanical stress in interconnect system and the diffusion of vacancies. During fabrication, we fabricate layers after layer. The whole process need to go through many thermal cycles. For these steps, once temperature is at high level, then again cool down, then again high level. So metals, not only single metal layer, there are multiple metal layers. So metals basically, those metal layers goes to high temperature and again cool down. Although there are different types of materials, how they behave under temperature or thermal cycle, how they expand, how they relaxes, that is not identical because materials are different. There is this thermal coefficient is different. This thermal expansion of metal and dielectric, these are completely different. So the existence of thermal stress in the interconnect is caused by thermal expansion mismatch between the metal and the surrounding materials. Surrounding materials like there are oxide layers, there diffusion barriers, silicon substrate, all different things are there. The BOL interconnect structure consists of several different materials like metal, dielectric, diffusion barrier, silicon substrate and capping layer. Fabrication of the structure involves several thermal cycles from room temperature to above 400 degrees centigrade. A large amount of stress can be introduced due to thermal expansion mismatch among these materials. Now, metal expands due to heating and then contracts during cooling process, although unable to retract to the original since the metal is constrained by the other material. As a result, there is a tensile stress in metal layer. Now, metal atoms moves to balance stress condition, thus void is created. Now this metal when cool down after high thermal cycles, they don't get back to its original situation because now metal is surrounded by other materials also. So there is a tensile stress created in the metal layer. Now metal atoms move to balanced stress condition. Thus void is created. Now void in metallization tends to nucleate and grow around the vias and block the flow of electrical current due to open circuit condition. Void diffusion is shown here. The void is moving here and continuously void this creates, they nucleated, they create a bigger void. Void creation just below the via, that means current cannot flow here. This is a void area. There is disconnection, that is open circuit. So it's creating an open circuit condition and current will not flow. If current is not flowing from there, so its circuit is not working in proper way, it lead to failure. Now this is stress migration. We are done with this slide. We will move to the next slide. Now CMOS latchup. CMOS latchup is also another failure reason. We have a detailed episode on CMOS latchup. We have an article on that also. Both the link is provided in the description. You can watch the detailed episode and read the article. A latchup is a destructive short circuit phenomena, the CMOS structure. It can be defined as a low resistance path between voltage levels. It caused by low impedance path between power supply, rails of MOSFET circuit through PNP and parasitic structure underneath. The structure is here an N plus zone, then this P substrate, then here N well, that is NPN, and in this way also P plus zone, N well, and here it's P. So PNPN structure is getting here. Two back-to-back transistor is forming a PNPN structure, NPN and P. The circuit function is disrupted by latchup and currents are frequently large enough to cause permanent damage. The parasitic PNPN structure resembles an equivalent to silicon control rectifier structure. And we know in silicon control rectifier or SCR, is sudden huge current flows. This is the characteristics, IV characteristic of SCR. So a PNPN structure which created by PNP and an NPN transistor stacked next to each other. Immediately after latchup trigger, one of the transistors starts conducting and the other one begins to follow it by start conducting. They both stay in saturation for as long as the structure is forward biased and some current flows through it. This is not the desired path of flow of current, although this parasitic PNPN structure, huge current flows, and this can lead to CMOS failure. We are done with this slide. We will move to the next slide. Now, electrostatic discharge. ESD is the release of stored static electricity. The most famous ESD in large scale is lightning. ESD event that take place in chip is not visible. ESD destroys about 20% of electronic components before they are installed into a system. Even before installing in a system, that is destroyed by ESD. ESD may only damage a component, but it leads to further subsequent damages within brief time during circuit operation. If a component is damaged, again its performance gets subsequent damages within brief time during a circuit operation. So a person can acquire charges by simply walking across a room. When such a charged person or object then approaches an IC, an ESD event occurs, characterized by high current within few nanoseconds. A high current density and or electric field can damage conductor, semiconductor and insulator in an IC. High current within very short period of time, few nanoseconds, can damage an IC. Electrostatic straps are used in industry to protect from ESD where electronic circuits are packaged and assembled. The circuit present inside the IC will tend to be partially damaged or might break down when this high voltage pulse enters. When we buy different semiconductor components for computers, we get it in a dark gray package. We all have seen that. That is external protection for ESD event. ESD in an IC is usually start with oxide breakdown which result in percussion path. The high current density damages the semiconductor devices through thin film fusing, filamentation and junction spike. The high electric field on the other hand can cause failure through dielectric breakdown or charge injection. So ESD is a very prominent condition where a device might lead to damage. Within a very short period of time, huge current flows. So we are done with electrostatic discharge and actually we are done with today's discussion. Today we have discussed about different reasons which may lead to chip failure. So we are done with today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any dislike, put it as a comment. If you have a query or question, also put it as a comment. Thank you again and bye for today.